Welcome back. In green energies, we have different ways of extracting energy which are not harmful to environment. So one of them is ocean thermal energy conversion system or OTEC system. In this kind of system, if you are able to create a temperature difference of around 20 degree, then you will be able to economically produce electricity with the help of this kind of system by utilizing the heat energy available in the warm surface water and the deep sea water. The surface water will be warmer because it gets heated up by the sun, but the sun rays are unable to reach the depths in the ocean. So if you go around 2 kilometers below the surface, there the temperature of water will be around 4 degrees Celsius. Approximately it will be around 4 degrees Celsius. So if I consider the surface temperature to be around 25-27 degrees Celsius depending on the location and the season. So if the surface temperature is around 27 degrees Celsius and the deep sea water, which is at a depth of around 2 kilometers, is 4 degrees Celsius, then we have a temperature difference of around 23 degrees Celsius, which can be utilized to economically produce electricity throughout the day. So the utilization of such temperature difference or such heat source and sink, we call them as ocean thermal energy conversion system, because we are utilizing the thermal energy which is available in the ocean and we are converting that into useful form. There are two such systems where we can utilize the ocean thermal energy and convert that into electricity. The first one is open cycle or Claude system, and the second one is closed cycle or the Anderson cycle or Anderson system. Now let us go through each of them. In the first one, which is the open cycle OTEC system or Claude system, what we have here is we have an evaporator, or this is also called as flash evaporator. So here we are not supplying any heat energy to evaporate water. What we are doing here is we are reducing the pressure below the boiling temperature of the water at that given condition. So if the water temperature is around 27 degrees Celsius, then the pressure or the saturation pressure is around 0.035 bar. So if you take the pressure below that, then at 27 degrees Celsius itself the water starts to evaporate or starts to form steam. That low pressure steam can be passed through a turbine which converts the thermal energy available in the steam into mechanical energy, and this can be coupled to a generator which produces electricity. So in this diagram, so we have the block diagram of open cycle OTEC system. So the major components here are the evaporator, vacuum pump, turbine, direct contact condenser and a pump to supply cold water from the depths of the ocean. So here first what we do is we pump surface warm water which is around 25 to 27 degrees Celsius depending on the time of the day and the season. So the warm surface water enters the flash evaporator where we drastically reduce the pressure of the water. So thereby converting a part of water into vapor, and to reduce the pressure we have a vacuum pump here. The function of vacuum pump is to reduce the pressure and also to remove non-condensable gases which may increase the pressure of which may reduce the pressure of the steam. So the vacuum pump, this is the vacuum pump that creates a very low pressure inside the flash evaporator, and at the same time when the pressure reduces, the dissolved gases will be discharged and the vacuum pump will take away the dissolved gases and it leaves only the steam to pass through the turbine. So from here the steam enters the turbine, where the steam transfers its energy to the blades of the turbine, and the fluid energy gets converted into mechanical energy. From here, the steam enters the direct contact condenser. So for a turbine, the pressure difference across the turbine is the amount of energy which we can extract. And since we are using a flash evaporation system here, the pressure of the steam when it enters the turbine will be lower than the atmospheric pressure. So we need to maintain still lower pressure. So for that purpose, we have a condenser here. If the pressure was above atmospheric pressure, then we could have left that to the atmosphere directly, but the pressure is at the entrance of the turbine itself will be lower than the atmospheric pressure. So we need to have a direct contact condenser where the cooling water comes from the ocean depths. So the cold water from the depths of the ocean at around 4 degrees Celsius enters the condenser, and it will be sprayed over the steam coming out of the turbine. That condenses, the steam absorbs, cooling water absorbs heat from the steam, and the steam gets condensed back into liquid water that maintains a low pressure at the end of the turbine. And that slightly warmer water which is coming out of the condenser will be left back to the surface of the ocean. So this is the working of an open cycle OTEC system. Since we are using steam here which is below atmospheric pressure, we need to have a very good tight seal in all the places where we have low pressure steam. Otherwise the atmospheric air can enter the pipeline or the turbine, and that reduces the pressure or the energy which can be extracted from the steam. So that is the major drawback in this kind of system, and the amount of energy produced here will also be not very high. So that is another major drawback. Because of that, generally we don't go for open cycle OTEC system. So the second method is closed cycle OTEC system or Anderson cycle. So in closed cycle OTEC system, instead of having a flash evaporator, what we have here is a heat exchanger. So what we do here is we take surface warm water which will be at around 25 to 27 degrees Celsius, and that will be passed through the boiler. So boiler is a heat exchanger where the surface warm water exchanges heat to another working fluid. So here the working fluid can be ammonia, can be propane, or can be freon, which has very low boiling point. So the advantage of having the refrigerants as working fluid here is they have low boiling point. Because of that, we can increase the pressure. By increasing the pressure, we can increase the energy conversion efficiency. Okay, and it will be easy for us to maintain the system because it is above atmospheric pressure. But here we need to have proper sealing in the turbine, at the inlet and outlet of the turbine, at the exit of the flash evaporator, as well as at the entrance and outlet of the condenser. But here, since it will be working above atmospheric pressure, it is easy for us to maintain this kind of system. So what we do here is we supply heat energy to the working fluid with the help of the warm surface water. So the warm surface water will be passed through the boiler, and here the liquid ammonia will be flowing, and that absorbs heat and gets converted into vapor ammonia or vapor working fluid. That vapor passes through the turbine and transfers its energy to the turbine blades and thereby converting the fluid energy into mechanical energy, and then that vapor which is coming out of the turbine enters the surface condenser. So it's there will be no direct contact between the coolant and the vapor in this case. In the case of open cycle, we had a direct contact condenser where the water, the cooling water was sprayed directly over the steam coming out of the turbine. So there was direct contact between the two working fluids, that is the hot fluid and the cold fluid. But in this case, we have a surface condenser where the cooling water pumped from the depths of the ocean, which will be at around 4 degrees Celsius, that passes through the pipe, and the vapor flows over the pipe and transfers its energy to the cooling water and gets condensed back into liquid working fluid, and that will be collected at the bottom, and then again it will be pumped to the boiler with the help of a liquid pump. Okay, so here the main advantage here is we are using a pressurized system, so the efficiency of energy conversion is more when compared to open cycle OTEC system, and also here it is easy for us to maintain the system. So after the warm water supplies transfers its energy to the ammonia or other working fluid, the water will be discharged back to the surface. So this is the working of closed cycle OTEC system or Anderson cycle. Another way of utilizing green energy is utilizing the geothermal energy. Here we have geothermal energy conversion systems. So before going to the different systems through which we can utilize the geothermal energy, first let us see how we get the geothermal energy. So here we have a cross section. Here we have the core of the earth, and then we have just above that we have the igneous rock. The core of the earth will be very hot, and the heat will be supplied to the igneous rock. Rocks are very bad conductors, so it takes longer duration to heat the igneous rock. And above the igneous rock, so here we have reservoirs. So reservoirs are nothing but empty spaces where the groundwater has trapped. Okay, above that we have impermeable solid rock, so the water cannot escape from the ground. So if there are any places in which at the bottom as well as at the top you have rocks where there are no gaps, and if the groundwater gets trapped in that place, then what happens here is the water will be continuously heated by the heat supplied by the igneous rock, where the igneous rock gets heat from the core of the earth. So the water gets continuously heated here and its pressure keeps on increases. Due to very high pressure, there will be spots in the impermeable rock where it has a weak, where the rock is slightly weaker. So if there are such spots, then what happens is a crack will be formed because of very high pressure water which is present here in the reservoir. The pressure of the water increases because it is being continuously heated. So because of that, the pressure of the water increases and that forms fissures. So fissures are the naturally occurring cracks in the rocks. So through the fissures, so the hot water can come in the form of steam in the fumaroles, or it can come in the form of hot water through the wells or in the form of hot springs. These are the naturally occurring geothermal sources where you can utilize hot water or steam and convert that into some useful, convert the energy available in them into some useful form. But if you want to create a plant, or if you want to utilize it by force, then or in artificial means, then what we do is we locate a suitable place where we have the reservoir, or the mantle or the core is very close to the surface. So if you have sufficient amount of heat energy available, then we can artificially create a well, and we can create cracks within the rock, and we can create an artificial reservoir, and we can supply water into the reservoir. that water gets heated up, and once it gets heated up we can bring it back to the surface and utilize that energy available in the water. The water may, depending on the temperature of the igneous rock, the water can be in the form of vapor or in the form of liquid. So we can utilize that energy available in the water and convert that into electrical energy. So this is site specific. So you have to first locate the site where the mantle is very close to the surface, and you can utilize a very large amount of heat energy. So there you can drill a well, and there are several methods to create cracks in the impermeable rock. And once we create cracks and then once we supply water to that, the rocks which come in contact with the water will become slightly cooler than the surrounding rock, and that creates that helps in the propagation of the crack. So that we call it as thermal cracking. So that creates still more cracks, and crevices will be created through which the water can penetrate and absorb heat. Again, those crevices gets cooler, and that initiates further crack in the impermeable rock system. Okay, that is how we can create or we can utilize the energy. And for drilling the hole and initiating the crack, we have many methods. So once we drill the hole, then either to create the reservoir, what we can do is either we can use very high pressured water, that we call it as liquid cracking. So using very high pressured water we can create cracks and we can form a reservoir, or we can use nuclear explosion inside the well and we can create reservoir, or we can use regular explosives such as TNT inside the well and we can create the reservoir. So the reservoir can be formed in any ways. Generally we don't prefer nuclear explosion because that contaminates the water, and we need special equipments to handle the water, special heat exchangers to handle the hot water or steam coming out of the well. So we prefer hydraulic cracking, which is with the help of high pressured water, or regular explosives to create an artificial reservoir. That is, if you don't have a reservoir, natural reservoir in that place. Okay, then we can supply water to the reservoir and we can absorb heat energy, and we can bring that water back to the surface in the form of either hot water or vapor, depending on the heat energy available from the core, and then we can convert that into useful mechanical energy or electrical energy. Now let us see the different ways in which you can convert the heat energy available in the earth into useful form. There are three major ways in which you can convert heat energy available in the earth into useful form. The first one is hydrothermal, where you are using water as the working fluid to absorb heat energy, and that will be converted into mechanical or electrical energy. So in hydrothermal we have two methods. The first one is vapor dominated method, where majority of the portion coming out of the well is vapor. So that vapor can be cleaned because it is coming from earth. There can be sand particles or small rock particles or some other solid particles, and we need to clean it before we supply the steam to the turbine. So that is the vapor dominated system, and then we have liquid dominated system. If the conditions here, if the temperature of the igneous rock are not very hot, then we can bring back the hot water and use that as heat energy or heat source to heat some or to create vapor of some other working fluid, and we can utilize that to produce electrical energy or mechanical energy. So that is liquid dominated system. Then we have geopressurized system, and we have petrothermal or hot dry rock system or HDR system, where we have very hot rock but we don't have any water. So in those kind of places we need to create artificial reservoirs, as I explained here, by drilling the well and then using hydrocracking or using explosives or nuclear explosion. We need to create artificial reservoir, and then we can utilize the heat energy available in the hot dry rock or the petrothermal. So now first let us see the hydrothermal. In that we have drawn here the schematic of vapor dominated system. Let us see the working of vapor dominated system. As I said here, first we will have a well through which we will be drawing hot vapors out of the geothermal source. Okay, so we have the well through which the vapor comes out of the well, and here we have a valve to regulate the amount of vapor that is supplied to the centrifugal separator and the turbine. So the vapor passes through the centrifugal separator. Here the vapor will be passing through a conical structure where it creates a centrifugal force as it passes through the conical structure or the centrifugal or cyclone separator, and the heavier particles, the solid particles which are present in the steam, it may be sand particles, mud particles, or small rocks or some other solid particles which are present or which are carried with the steam, they get separated and the clean steam will be supplied to the turbine. A part of the steam will be supplied to the turbine and a very minor fraction will be supplied to steam jet ejector. So we will come to the function of steam jet ejector later. So majority of the steam passes through the turbine, where the heat energy available in the steam gets converted into mechanical energy, and that is coupled to a generator which produces electrical energy. After the steam passes through the turbine, and here we have drawn the turbine in this manner. The steam is entering at the smaller end and leaving at the larger end. This is because steam, when it enters the turbine, it will be having high thermal energy and its specific weight, specific volume will be small. As it expands, its specific volume also increases, and since turbines are turbo machines and all turbo machines are steady flow devices, so to maintain a constant mass flow rate, we need to increase the flow area as the steam expands. So you have to write the turbine in this manner only. If you provide the input at the larger end and output at the smaller end, then it becomes a pump or a compressor. Okay, sorry, it becomes a compressor. For a turbine, always the inlet should be at the smaller end and outlet should be at the larger end. The steam coming out of the turbine, now we need to condense it before re-injecting that into the geothermal source or into the well. So we have a direct contact condenser, and the cooling water will be supplied to the direct contact condenser with the help of a cooling tower. What happens here is we need to maintain a low pressure, and we can maintain the low pressure by reducing the by converting the vapor at the end of the turbine into liquid water. So when you are doing that, the steam, it's not the steam produced in a boiler, it is the steam coming out of the well or the geothermal source. So it also contains some dissolved gases or non-condensable gases with it. So if we have non-condensable gases here, then that increases the pressure instead of reducing the pressure at the direct contact condenser. So we need to remove those gases, the non-condensable gases which are mixed with the steam coming from the well. So what we do here is we use steam jet ejector. The function of the steam jet ejector is to remove non-condensable gases from the condenser. So here this works because we are supplying high pressure steam into the steam jet ejector. So as the steam jet passes through the ejector at a high speed, that also pulls gases which are non-condensable gases which are present in the condenser with it, and that will be exhausted to the atmosphere. So the non-condensable gases and a part of the steam will be left to the atmosphere, and that with the help of the steam jet ejector we can remove non-condensable gases from the condenser, and thereby we can maintain a lower pressure at the end of the turbine. Otherwise, if the non-condensable gases are present here, although a part of the steam gets converted into liquid water, that space will be occupied by non-condensable gases and we will not be able to maintain a very low pressure at the end of the turbine. So after the water gets condensed, so that water will be pumped to the cooling tower with the help of the condensate pulp. So if the amount of water is very high, then a part of the water can be supplied to the cooling tower and the remaining pump water can be re-injected back into the well. So now whatever the water enters the cooling tower gets cooled as it passes through the cooling tower, and that will be taken out, the cooled water will be taken out, and a part of that will be sent back to the condenser to act as cooling water, and the remaining is re-injected into the geothermal source with the help of re-injection well. So this is the working of an vapor dominated system or vapor dominated geothermal energy conversion system. So here what we do is we take out the vapor dominated fluid, we take out the vapor from the well, and that the amount of vapor will be controlled with the help of a valve, and then it enters a cyclone or a centrifugal separator, where as the fluid passes through the cyclone or centrifugal separator, it moves in a circular pattern. Because of that, centrifugal force will be created on the solid particles which are suspended in the steam, and they are removed from the centrifugal separator. Now the clean steam enters the turbine. Majority of the clean steam enters the turbine. A part of the steam will be taken out to aid the removal of non-condensable gases from the condenser with the help of steam jet ejector. Okay. Then as the steam expands through the turbine, as it transfers energy to the turbine blades, the steam comes out of the turbine at a lower pressure. So the amount of energy extracted from the turbine will be directly proportional to the pressure difference across the turbine. So we need to reduce the pressure at the end of the at the end of the turbine. We cannot increase the pressure here because that is decided by the conditions at the geothermal source. But what we can do is we can reduce the pressure at the end of the turbine, thereby increasing the pressure difference and extracting more amount of work from the turbine. Okay, so to reduce the pressure, we need to condense the steam coming out of the turbine. To do that, what we do is we use a direct contact condenser and we supply a part of cooling water, a part of water coming out of the cooling tower as cooling water, and we directly spray it over the steam. So the direct mixing of steam and water results in condensation of the steam, and the liquid water will be drawn with the help of condensate pump and sent to the cooling tower. If the amount of water is very high, a part of that will be supplied to the alternate re-injection well, otherwise the entire water enters the cooling tower. From the cooling tower, the water as it passes downwards in the cooling tower, it gets cooled, and that water, a part of that water will be supplied as cooling water to the direct contact condenser, and the remaining water is re-injected with the help of a re-injection valve into the geothermal source, so that we can extract more amount of energy from the geothermal source. So this is the working of vapor dominated geothermal energy conversion system.